Good morning. Hello, analysts. So, I'm finding myself slightly behind schedule, and so I'm preemptively pre-recording a few of the things from the unit titled The Order of the Real Numbers. And in particular, I want to dig right into some stuff on induction. So I'm sure lots of you have done some things with induction before, which is why I feel comfortable doing this way. So let's talk about what induction says. So let's review just the proof technique of induction. So here's a proof technique. Let P of n be a statement which makes sense for every natural number n. P of n might be 3n minus 1 is even. It might be 1 is bigger than or less than or whatever, x to the n. There's some setup before that. If you can prove that the statement is true when n equals 1, so in this case, if you can prove that x to the 1 is less than 1, and you can prove an inductive step for every natural number n, P of n implies P of n plus 1. In this case would be let n in n. If we can assume x to the n, that should probably be greater than 1. That's what erasable pens are for. If we can assume x to the n is bigger than 1 and prove that x to the n plus 1 is bigger than 1, then we'll be able to conclude that for every natural number n, P of n is just true. Cool. And you know the intuition for why that should be true. Well, you prove P of 1, and you know that P of 1 implies P of 2. So P of 2 is true. But you know P of 2 implies P of 3. So P of 3 is true. And so on. And there's the intuitive reason why induction works. Let's use it to do something. So here is a claim. And maybe there's some setup before the claim too. Definition. Let f be a field. For any x in f and any natural number n, I'm going to define x to the n recursively. So there's going to be some recurrence relation. I'll give you some base case how x to the n should behave. And then a description of how x to the n behaves, which depends on the previous terms. X to the n is defined recursively by the rule x to the power 1 equals x. Sounds right? And if I want to compute x to the n with n bigger than 1, I'll take x to the n minus 1, which by recursion I can compute, and then I multiply that by x. And of course, just think through intuitively, that means x to the 1 is x, that's by assumption. That's by the base case of the recursive definition. X to the 2, well that's x times x to the 2 minus 1 is 1. Yeah, that's x times x, which is what you expect. X cubed will be x times x times x, and so on. So the upshot is, now we have a very formal, rigorous definition. I can now use induction to prove things. And let's just do one example. Let f be an ordered field, a thing that we've talked about, and n be a natural number. If x is bigger than 1, then every power of x is also bigger than 1. Let x be an element of the ordered field and n be a natural number. If x is between 0 and 1, then so is every power of x to the n. If x is equal to 1 and n is a natural number, then 1 is, of course, equal to every power of x. So let's go through and we'll just prove each of those in the time that this recording will take. Right now I've taken about 4 minutes. So let's do it. Let's prove these claims. I'm going to start with claim 3 because that's the one that looks like it's the easiest. Let's let f be a field and x be equal to 1. The base case, I just need to show the claim when n equals 1. We must show that x to the 1 equals 1. Well, by the recursive definition, x to the 1 is equal to x. By assumption, That's right, we assumed x is equal to 1. X is equal to 1. Thus, x to the 1 equals 1. Completing the proof, at least for n equals 1. Inductive step. Let's now consider any natural number n. I'm going to assume that x to the n equals 1. So I'm fixing a natural number. I'm assuming that the thing I want to show is true for this fixed natural number. Not for every natural number, for this fixed natural number. I now need to show that the claim is true for the next choice of n, for n plus 1. So notice, like, I'm not saying anything like, hello. So let's proceed to do that. And there's our recursive definition here. All right. By the recursive definition, what is x to the n plus 1? It's x times x to the n. All right. Let's see. There are two things that I can think about now. I know what x is. It's 1. I know what x to the n is. It's 1. So let's just write down both of those. By our inductive assumption, x to the n equals 1. We also assumed x equals 1. So x to the n plus 1 is equal to 1 times 1, which is equal to 1, the last equality follows from field axioms. In fact, let's be more vague than that. Follows as f is a field. All right, just something indicating that it's just true because of algebraic facts. So, what have we done? We've shown that the thing that we wanted to prove is true when n equals 1. We've shown that if we assume that x to the n equals 1, then x to the n plus 1 equals 1 for any fixed n. So, what can we conclude? We can conclude by the principle of mathematical induction that the thing we want to prove is true. If x is equal to 1, then x to the n is equal to 1 for every natural number n. And ideally, what you'll do now is you'll stop this recording, and you'll say, well, I know how to do the other two claims, and you'll just do them on your own. But I've got enough time that I can continue this recording for a bit. Let's do some more induction. Let's let f be an ordered field and x be bigger than 1. Or maybe I should recall claim 1. Claim 1. If x is bigger than 1, then x to the n is bigger than 1 for all n in n. So, base case, we have to show that x to the power 1 is bigger than 1. And again, this is like one of the obvious ones. Usually the base case is the easy case. Sometimes it's not. Let's do it. Let's see. By the recursive definition of exponentiation, x to the 1 is equal to x. Good. By assumption, x is bigger than 1. So, x to the 1 is in fact bigger than 1. Inductive step. Let's fix any natural number n. We will assume that x to the n is bigger than 1. We need to show that x to the n plus 1 is bigger than 1. And, well, let's do that. It's going to look pretty similar to what's up here. By our recursive definition, x to the n plus 1 is equal to x times x to the n. And what do we know now? We know x is bigger than 1. We know x to the n is bigger than 1. And let's just think strategically about what we can do. So we have some stuff about how inequalities behave under multiplication. This will be filled out by the time you're actually watching this. If A is less than B and you multiply it by a positive number, the inequality gets resolved. So, let's think about that. Well, x is bigger than 1 is bigger than 0. So let's see. X times x to the n. I know that this is bigger than 1. I know that that's bigger than 0. Let's see, so that should just be bigger than x times 1. Right, x to the 1 bigger than 1 becomes that when I multiply both sides by x. Ooh, but I also know x is bigger than 1 by the assumption in this case. So let's use that. By our inductive assumption, x to the n is bigger than 1, and x is bigger than 1, which is bigger than 0. So, by, well gosh, that claim was called multiplicativity. Of inequalities, x to the n times x is bigger than 1 times x. Maybe I'll even put the is equal to x here. By assumption, x is bigger than 1. So, let's put this all together. X to the n plus 1 is equal to x times x to the n. We've shown that that's bigger than x is bigger than 1. So by transitivity, x to the n plus 1 is bigger than 1. All right. Carrying on. So let's prove this last claim in the theorem. Let's let f be an ordered field. Let 0 be less than x to be less than 1. And maybe off to the side I'll put the thing we want to show. The goal now is 1 is less than x to the n. Nope, 0 is less than x to the n is less than 1 for every n. So, let's do that. Base case, we have to show that 0 is less than x to the 1 is less than 1, and this is going to be the same thing again. By the recursive definition, of x to the n, x to the 1 is of course x. By assumption, 0 is less than x is less than 1, so 0 is less than x to the 1 is less than 1 as needed. Alright. Inductive step. We will now fix any natural number n, assume the thing we want to show is true for that fixed n, and prove it's true for the next one. And you know what I'm going to do. X to the n plus 1 is equal to x times x to the n by the recursive definition. And let's see. Looks like I have two inequalities to prove now. One that this thing is bigger than 0, and the other that it's bigger than 1. Nope, less than 1. So let's false check that it's bigger than 0. By assumption, 0 is less than x. By the inductive assumption, zero is less than x to the n. And now let's see. So that says that x is positive and x to the n is positive. I need x times x to the n is positive. Oh, well, gosh. by the closure of the set of positives, which recall is just one of the axioms. X times x to the n is bigger than 0, so x to the n plus 1 is bigger than 0. Of course, we're not done, even though I've used up all my space. I need to prove the other inequality. So, let's study that. So, this time I have 0 less than x less than 1, 0 less than x to the n is less than 1. I need to show that the product is less than 1. Well gosh, I know that x is bigger than 0, so I can multiply both sides of this inequality by x. So x to the n times x is less than 1 times x. Oh cool, but that's less than 1. So let's just do that. As x to the n is less than 1 and x is bigger than 0, we may multiply by x to see that x times x to the n is less than x times 1. Oh cool, that's x. By assumption, x is less than 1, so we conclude x to the n plus 1 is less than 1. And this sentence is now in the wrong place, so I'm just going to rewrite it. Thus, by mathematical induction, we conclude if 0 is less than x is less than 1, then for all n in n, 0 is less than x to the n is less than 1. This completes the proof. And let's put the nice little Halbos box there. Cool. So this and a few more short recordings will appear on the web page probably before class happens. We'll talk through what we talked through in class, and then these will be up, and you can decide how much you want to see. All right, see you tomorrow.